My name is Paul Williams,
And I'm Alex Lucente.
and we're with the ACT Lab presenting our project, The Synthesis and Analysis of Alpha-Humulene. Our project is to study the components of beer relating to the hops within, specifically in IPAs, which are more bitter than regular beer. The bitter flavor is caused by the hops, and within the hops there are these terpenes such as alpha-humulene. Different terpenes are natural compounds found in herbs that you've heard of, such as ginseng, cannabis, and sage. When oxidized for our purposes, the alpha-humulene creates this bitter flavor.
So the IPA beers specifically are largely associated with the oxidation of alpha-humulene because the oxidation states of alpha-humulene, like as you can see, these epoxides or ring formations that form off the double bonds, that makes the beer even more bitter than it would otherwise be with just generic hop brands. And then so far with our synthesis that we've done to make the alpha-humulene itself for our own purposes of study, we have added several protecting groups onto our starting material, which is an alcohol called farnesol. We have added a tert-butyl diphenylsilyl ether here. We have added a benzyl alcohol protecting group, and we've added a tosyl chloride protecting group. And then after all of these steps, we have done a ring formation on the, well, it's actually the most distal double bond here, where we use these reagents here, and we add a strong base, and we get a epoxide. And you can see on the NMR that we have so far, NMR shows us the relative positioning of protons relative to other protons on the molecule. You can see that the peaks I have highlighted here correspond with the hydrogens where we'd expect them. We used a NMR predicting tool to properly identify where these peaks should be, and they did correspond very well to what we had predicted. So for instance, we have these blue hydrogens here that correspond to these peaks. We have these yellow hydrogens on the aromatic ring of the protecting group that correspond here. And then after this step, we did epoxidation. And so far, we haven't got a good result for the epoxidation, at least not with NMR showing us anything. That could be due to improper column chromatography or flash columns, any type of purification method, really. And we're just not getting the peak where we would expect it for the epoxidation ring.
So for our quantification study for the humulene, we first wanted to create a calibration curve using a humulene standard. Next, we wanted to find the alpha-humulene within hops and beer, specifically the IPAs. There's different hop types, so we used one called Mosaic, and there's different IPAs. The brand we used was Good Behavior. So we use a mass spectrometry gas chromatography, which allows us to find different terpenes based on their mass. So this is you can see the alpha-humulene to the far right in the green. It's a very small peak. To see other terpenes that are within the hops, you have beta-caryophyllene and beta-myrcene highlighted in the blue and pink. For the IPA, when we were doing liquid-liquid extraction with DCM, we seem to have washed out all of the other terpenes, and the only one we were left with was alpha-pinene. So for future work, we have about 7 steps left within our synthesis. Once we're finished with that, we hope to use the lab-made humulene and do GC on that to quantify it. Next, we want to oxidize the alpha-humulene. It oxidizes in things in the atmosphere such as ozone, nitrous dioxide, and even oxygen gas because it's very volatile. Over time, the alpha-humulene being oxidized should replicate what it is like within IPA brewing.
Thank you.